same. Total voltage drop, total amount of energy lost, and the total voltage gain, the total amount of energy gained, will have to add up to 0, which means that the amount of energy supplied and the amount of energy lost will have to equal to each other. This statement is the conservation of energy. So that little thing that we just did is known as the conservation of energy. So Kirchhoff's voltage rule is simply the conservation of energy. All right, so this happens because of the conservation of energy. So the amount of voltage supplied by the battery and the amount of voltage drop, energy lost, has to be equal to each other. All right, so this one is straightforward, obviously. All right, so the only thing you have to do is just solve for I. All right, so voltage terms are going to be on the left. I'll get to current on the right, solve for I, and then you're done. I don't know what the numbers are, and they're not that important. What's important is the way to do this problem. All right, that was fun. Okay, so this was straightforward. This was a good example. Okay, this is how the problem is done, straightforward. Let's work on this problem. This is the current going across the headlights, coming out of the battery, coming out of the alternator. So you need to generate 3 equations in order to solve for 3 unknowns. Okay, so numerically, this is a little bit too complicated, so we'll just focus on generating 3 equations. In terms of generating 3 equations, let's go back to the lecture notes. Okay, so this is the Kirchhoff's voltage rule based upon the loop rule. The next one is the junction rule. All right, so the junction rule simply stated, here's your junction. This is the current going into the junction. This is the current going into the junction. This is the current coming out of the junction. All right, the total current going into the junction is going to be the same as the total current coming out of the junction. If it's going into the junction, we'll add them up. This is positive, this is positive. So which means that the current going into the junction is going to increase. Current leaving the junction is going to decrease. So the increase of current, just sum up the current values. And the current is decreasing, so this is going to be negative. All right, so the total current going into the junction and the total current leaving the junction, they will sum up to 0. This comes out of the conservation of charge. All right, so this is the conservation of charge. And the total voltage drop and the voltage gain is the conservation of energy. So the loop rule is based upon the conservation of energy. Junction rule is based on the conservation of charge. Loop rule is the Kirchhoff's voltage rule, and the junction rule is otherwise known as the Kirchhoff's current rule. This means current. All right, so junction rule is the same as the Kirchhoff's current rule. Loop rule is the same as the Kirchhoff's voltage rule. Current, voltage, voltage, current. All right, so let's focus on this one. Let's make this larger. All right, so the only thing we have to do is just come up with 3 equations. I think I can come up with 4 equations easily. All right, the first one is going to be straightforward. I'm going to apply the junction rule. All right, so I'm going to apply the junction rule to junction B. All right, so there's current going in this direction, so that's your current A. There's current moving in this direction, so that's your current B. And notice that the current is leaving the junction. This is the current H. All right, so current from the battery, current from the alternator. This is going into the junction, so this is plus. This is going into the junction from the battery. This is plus. The one that's going into the headlights is leaving the junction, so that's going to be negative. All right, so 4 equations, that's all we need. 3 equations, I can generate 4. All right, applying the junction rule to point B. All right, so the current from the alternator is going to the junction, so that's positive. From the battery going into the junction, that's positive. Headlights leaving the current going through the headlights is leaving the junction, so that's going to be negative. So current from the alternator, positive. Current from the battery is positive. And the current going through the headlights is going to be negative. They will add up to 0. So this becomes my first equation. All right. Okay, so let's come up with 2 more equations. Just for the hell of it, I'm going to come up with 3. So let's come up with 2 more at the very least. All right, I'm going to apply the loop rule to this segment. All right, so I'm going to loop in this direction. I'm going to loop in the clockwise direction. All right, so I'm going to start at point B, go up, and then go back to the same point. All right, so we will go up. The current becomes the current through the headlights, which is going to go through the resistor. All right, so before I do anything else, as a general rule, I'm going to use symbols instead of numbers. All right, so here's the resistance of the headlights. All right, so I don't like using numbers. I'm going to call this the first battery. All right, so that's the car's battery. So the electromotive force due to this one. And I'm going to call this the resistance of the battery. So it's going to be R sub E. All right, so the current is going through the headlights right here. Current is in the direction of the loop. So there's going to be a voltage drop. So the current going through the headlights, through the resistor of the headlights is going to experience a voltage drop. All right, so this is my first loop. Loop is in this direction. All right, so, and then we will hit this junction. In this junction, the loop is moving in this direction. All right, so in the direction of the loop, notice that you jump from a low voltage to the higher voltage, so there's going to be a voltage gain. So there's going to be a voltage gain across the battery, so it's positive. All right, in this segment, we use a different current value. So this is the current from the battery. And current from the battery is along the same direction. It's moving along the same direction as the loop, so there's going to be a voltage drop there. All right, so here's the current from the battery across the resistor of the battery. Okay, so we're at this point, so we just looped around. So the total voltage drop and the voltage gain across the second loop is going to be 0. All right, so that's our second equation. We can come up with the third equation. This time we will loop around here. All right, so let's just change this one. All right, so I'm going to end up looping around in this direction. Once again, my preference is the clockwise direction. All right, so that's the direction of the loop. Once again, I'm going to start from here and then check to see what the voltage drops and the voltage gains are in this direction. All right, now notice that the current is moving to the left. My loop is going to be to the right there in opposite directions. So which means that whenever this current is looping in the opposite direction across this resistor, there's going to be a voltage gain. All right, so the current of the battery going through the resistor of the battery is going to be a voltage gain. The loop is pointing from high voltage towards the low voltage, so there's going to be a voltage drop here. All right, it's when we're here, we start to go in this direction, in the direction of the loop. There's going to be a voltage gain there. All right, so I want to name this epsilon 2. So across epsilon 2, there's going to be a voltage gain. All right, so the loop is moving in this direction. The current is moving in the same direction. So there's going to be a voltage drop right there. All right, so be mindful of the fact that this is the current from the alternator. And this is the resistance of the alternator. All right, so the loop complete, hit the junction point. All right, so this is your third equation. You got 3 unknowns, and the only thing you need is 3 equations. That's it. Can you generate one more equation just in case? If you had to, what would you use?
Oh, from the alternator through the headlight?
Okay, no, what would you use in order to come up with that fourth equation?
What do you mean?
You have to use the Kirchhoff's rules to generate the equation. So, which means that you have to come up with one more loop. So what would you use?
Around the whole thing from the alternator through the headlight.
Okay, perfect. All right, give yourself 5 points for that one. Yeah, you could, is that what you said initially?
Yeah.
Okay, you must have cut off because I heard half of what you said. Okay, cool, that's absolutely correct. All right, guys, you could come up with one more this time. You have to literally use the outside. All right, that's what you need to do. If that's the case, this is actually not bad. If you want to start from here, that's fine. So there's going to be a voltage drop here. There's going to be a voltage gain here. There's going to be a voltage drop here, and that's it. Voltage drop, voltage gain, voltage drop. So this times that is going to give you a voltage drop. You got your voltage gain because you're going from negative to positive, and this times that is going to be a voltage drop. Okay, so evidently in my head, I end up labeling everything. In reality, I forgot what the label was. Okay. All right, so let's do this real fast. So I'm going to start from here. You got a voltage drop. So this times that is going to give you a voltage drop. So that's going to be our equation number 4. All right, just want to, I need to use that space. All right, so this times that. Current for the headlights is going to be a voltage drop. All right, so there's going to be a voltage gain here from here to there. And there's going to be a voltage drop. This amount of current going through the resistor is going to be a voltage drop. And everything's going to end up to 0. Okay, so a couple of things to talk about at this point. Ooh, in real life, all right, so completely made up numbers in this case. So this is the amount of current coming out of the alternator, let's say, and this is the amount of current going through the headlights. And this is the amount of current coming out of the battery. All right, so these numbers are completely made up. I don't know what the actual numbers are, and I don't really care. Okay, so the only thing I'm going to focus on is the fact that this is negative, and the other ones are positive. All right, so what's the meaning of negative? What's the meaning of positive? Guys, when you're looking at a problem like this, in reality, when you're setting it up, notice that they already gave you in this problem the direction of the current. All right, so the current coming out of the alternator is going this way. The current coming out of the battery is going this way. These directions are assigned arbitrarily, randomly, okay? In the battery, notice that for whatever reason, the current is coming out of the positive, and then it's moving in this direction for whatever reason. All right, there's no logical reason to make the assumption that the current is going this way out of a battery, and there's no logical reason to assume that the current out of the alternator is going that way. So you randomly assign directions to the currents from these voltage sources. You could have easily said, hey, the current coming out of the battery is going this way, and the current coming out of the alternator is going in the opposite direction. It's actually just charging up the battery. You could have just easily come up with that assumption. All right, so you assign directions to the currents randomly. If the assigned direction is incorrect, when you do the algebra, it's going to give you a negative value. All right, so now learn how to interpret. In terms of physics, this is not big shit, but in terms of engineering, in physics, we're much more focused on the concepts and the symbols, but in engineering, the numbers do matter, and these positive and negative signs mean something. So which means that if I end up getting a negative sign for the current coming out of the battery, that means that this value is correct. Yeah, you will get 2 amps of current out of a battery, but the direction that I assign is incorrect. What that means is the current is not coming out of the battery in this direction. In fact, the current is going in the opposite direction out of the battery. That's what it means. So from the headlights, evidently the direction that I assigned is correct. And the current coming out of the alternator, well, that direction is correct, except the current coming out of the battery is not coming out this way, it's going out the other way. And all of a sudden, the mathematics makes corrections to your assumption.